Can you guys hear me? Oh, thank you, Joseph, for confirming. I was thinking like nobody is responding, so it looks like nobody is hearing me. So how you guys are doing? Very good evening, Joseph. How you guys are doing? What about weather? Is it good in your area? Thank you, Manoj, for responding. Ekta has joined. So I hope, guys, from the last class where we have started discussing about a lot of interesting questions, like we have gone for post iterations and in order traversal for with the iteration way. Already we have seen the recursion way, which was very easy, and we have also gone for iteration way, which was little bit looking like complicated, but that was also easy if we understood the logic. Very good evening, Arad and Ekta. Just started the class, waiting for people to join. Joseph has one doubt in find key recursive way. Sure, I will show you the code and we will go through. We will look into that one. Yeah. And Joseph, that code is not totally correct actually, because I will show you. I will show you what part of code is not correct there. I'm not saying it's not correct. It means we need to do little bit modification to run that code. So I will show you that thing. Okay. Okay, so yeah, so after understanding the iteration part, we also understood the BFS, right? And we have seen that BFS was very easy, right? We were just simply using one queue, inserting item from back into the queue, and then deleting it from the front side. And once we are deleting it, at that time we are checking that if that particular node has any child left or right, just push them from the back side, and then it's deleted from the front side. That's what we did. And the second way which we tried, that was about the label base, like how to find out the label. So for that, I remember whatever item currently available in the queue, just take the size of that and then do the size minus minus. Yes, height or label, yes. Then just simply do the size minus minus. So whatever loop you are running, that will provide you the label. There will be two loops, one loop for q dot length and second would be for size. So see, there is one like root node. That node will have two childs. So in the queue at the second label, two nodes will be there. So two times that iteration will run. So with that, we can easily understand how the labels work. Correct. And after that, we have solved some of the binary tree questions, like is symmetric, right, where we were trying to look for the mirror image. Second one, the find key, which Joseph has just now asked, how can we find key in the recursive way? Correct. That I think he is specifically talking about the code, but I'm hoping he has understood the logic, because it just you need to traverse whole binary tree, and at the before traversing every time, just check for that element. That if that element anywhere in the node dot value you find that element, it means that exists. That element exists in the tree. So that was the logic for that. And then I think we have gone for same tree as well. Like same tree and symmetric was very similar. In the symmetric, as we were discussing about, in the symmetric, we just put a one line in the middle of tree, and the left side and right side of same root node, left side and right side should match. If they both are matching, it's a symmetric tree. Or in the same tree, I think in your assignment you have a question for same tree as well. So in the same tree scenario, left side should match with left side, right side should match with right side, right child should match with right child, left child should match with left child for the same root. If that's the scenario, it means both are same trees. So that was all about the, I think we have discussed from the last class. Correct. In meanwhile, anywhere you have any doubt or wants me to go back into any of the logic again, I can quickly go into that. And today's topic, I'm thinking to start with zigzag question, which I already told you some logic also about the zigzag question. So I'm thinking to start with that, and then I think the second question of our binary tree, assignment, it was how to delete elements from the binary tree. Correct. So that's the second question we will see that. And in meanwhile, before that, you guys have any questions? So we can first look into that, and then we can start talking about the BST. So that's all. That's what going to be today's topics of discussions. So before that, let me first go for the find key and answer Joseph doubts. Okay, Joseph. In meanwhile, you can write your doubt if you have anything in that code. But meanwhile, let me go to that code. You guys are able to see my screen? Let me know in the chat. Today, actually, very less people has joined. I can see only 13 one. Only 13 has joined. Sir, for implementing a binary tree, the node insertion part is little tricky. Can you please discuss it briefly? See, for binary tree, insertion is actually, you know, because in the binary tree, there is no pattern to add. You need to explicitly tell Ekta that where, at which position you need to add. You need to tell explicitly. I will show you that thing. Let's first start with Joseph part, and then we'll come into the insertion part of this. Okay. So let me now first go to the find key one. I think it was in index.js only, right? Let's see if it's here. Yeah. So this was the find key code, right? So see, guys, what is happening here? I am first taking my root of node, like root of tree. So there is one tree like this. Let me also draw it quickly. Let me also open the one node. Line number 182. Yes, that's right. That's right, Likit. That's the only way we can go for. That's the only way for binary tree. Okay. So Likit has written very correctly, and I will show you also Ekta, and then we can see it quickly. Yeah. So let me open that. And okay, so like Joseph is saying he's just asking for any specific line. So let me go to that line 182, written left or right. Okay, so this is happening, Joseph. Let me tell you why. Okay, so this is a tree, right? Binary tree. So we have like 10 here, then we have 8 here, then we have 11 here, then we have 9 here, and then we have like 5 here, and then we have a 6. Correct? This is a binary tree for us. Okay, and we are looking for, yeah, so we are looking for number 5, number 6. We are looking for number 6. Correct. So we are looking for number 6. So see, so what we will do? What we will do here, Joseph? We will start with our root node, right? So first we will check, is the root node value is matching with the key which we are looking. This is the key we are looking. So we'll say no, this is not matching. If this is not matching, then what I will do? I will go for my left. I will go for my right. Okay. So first time I'm going for left. So you can see according to the code, you can see, as I'm finding it out, I'm just simply returning true from there. Yeah, that's fine. That's fine. Let's keep it like that. But you can see, first I'm going for the left side. Every time I'm going first for the left side, then I'm at the end, I'm going for the right side. So you can see, so first I will go for 8. I will check, okay, no, it's again not matching. Correct? Then I'm going for 11. Again, it's not matching. So you can see, in both scenarios, once I will not get anything, and then it will go for null scenario. Correct? Because at the end, node.left will become null. And then we'll come back to this condition. If node is equal to null, return false. Correct? So see, from here, it is returning false. Right? Right, Joseph? Are you able to visualize it? How things are working here? Yes. So till this line, for 11, this line has written as false. Correct? Okay, come back. Yeah. So for 11, this line has written false. Now it will go for right side. You can see in the code, right? So now for 11, it is going for right side. Correct? So where am I? Yeah, so now for 11 it's going for, again we will get null, so it will again return false. Correct, it will again return false. So again this will also return false, because left and right, you can see at the end the line 182, what that line is doing, it is just returning us whatever the result is in the left, whatever is the result in the right. So if both are false, so just return false. If any one of them are true, if any one of them are true, just return the true from there. So let me show you why we have done the or there. Why we have done the or there. Okay, why I'm not going to this one? Yeah. So see, yeah. So now you just consider there is also null, so it will also return false. So it will go for here, right? So left of 10 has given false to us. Joseph, you understood? Left of, yeah, so it is just returning true and false. So left of 10 has given false to us. So now we will go for the right side. In the right side, this is the 9. We'll again go for left, which is the 5. So again we'll see. And 5, these both again will be null null. So this will return false to this. But here of 6 left, this 6 will directly return true. This 6, you can see, we will uh, for the 6 we are not going into the left and right. You can see we are directly returning true once we are seeing the 6. So for 6 we are not going to the left and right. So for 6 these two operations will not happen, and we will returning directly return true from here. So false true will become true, and it will return. So now from the, for tens right is giving us true and tens left are giving us false. So false or true at the end will return as a true. So now key number 6 exists. That's what happening in the code, Joseph. We are checking for each node. For each node, we are checking left and right. Correct. And whatever result are coming, whatever result is returning, we are just returning back. Then that line number 182 is not required. No, that line number A 182 is the one. So line number 182 is the one who is just returning left and right result for any node. See, for any node, for line number 8, there are two nodes, 11 and 5, right? So that line number 182 is only returning us what result this node is giving, what result this node is giving. So like if this is 8, this is 9, this is 11. So this is left and this is right. So for 8, how we will identify the answer? For 8, how we will be identifying the answer? So line number 82 is only giving us left or right. If left is, this left is returning false, and if this 11 is also returning false, so here false or false. So for 8, answer would be false. So that's why line number 182 is the one who is giving us that. We are that doing in base case. We already checked in base case. Not able to get, not able to get it. What you're asking, Joseph? We are that doing in base case. No. In base case, we are checking for the key for which node it is matching. In base case, you can see in both base cases, we are checking where it is matching, but we are not getting the answer for any node. Yeah, we are so for null part is for leaf node. Null part, we are checking null part. Okay, so for null part, we are checking this node, right? For null scenario, the first base condition, checking this thing. If you are getting anywhere null, so you will return. Joseph, just see this tree. Again, see this tree, Joseph. 10, 8, 9, 5, and 6. Okay. And this is the 11. So Joseph, first, what you need to do? You need to find out that key exists or not. Find out that key exists or not. And your key is 6. Correct? That was your question? That was your question? Correct? So now how will you do that? How will you do that? You have to go to each node and find it out the answer for it. You have to go to each node and find out the answer for that. 8, right? Correct. So see, for each node, how will you find out the answer? For each node, okay. For each node, how will you find? For 8, how will you find out the answer? For 8, how will you find out the answer? So see, first what you are doing, you are running a recursion. In that recursion, you are checking if this node is equal to your key, it means this part of subtree can be an answer. This part of subtree is having an answer. Subtree having an answer. Correct? This part of subtree will having an answer. Correct? That's it. How you traverse? How you traverse? If you want to traverse a tree, how you traverse? You start with node, root node, and then you start traversing to the left. Then you start traversing to the right. Correct? And once you find it out, the answer here. Once you find it out your answer here, then you will what you will do. But still you are going to check for this one, right? Still you are going to check for that one. Yes, because see, because it's a recursion, might be this could not be our answer. So that's what actually is happening. At the end, at the line number 182, we are just checking left or right. If any one of them has having an answer, just return it. Just return our whole answer as a true. Understood? So see, left has given us true you, but if you are looking for 8, Joseph, so left will give you true because of second base condition. Because of second base condition, right? Yeah, because of this second base condition. Correct. But now you have to get the answer from right side also, right? Because you are traversing both. So for that you are doing this thing, line number 82. Understood it now? Yeah, because you are traversing both sides. So first you find it out the answer on the left side, you will also go for the right side. Okay, so Ekta is saying 11 will return true to line number 180 or 181. But as a whole, we need to return a final answer from 182. Right, sir? Or no, no, no. See, we are right now looking for, because while we are traversing any of the nodes, we are traversing left and right, both side of it. Then we are getting the answer. Correct? Because how the tree works, in tree we traverse through left and right. Correct? So now first we started with root node. First we started with root node. So in the root node, if we find out our answer, we'll not go left or right. You can see, if we find our answer in the root node only, if we are looking for, like, if this is our tree, 10, 8, 9, 11, 5, and 6. If we are looking for 10, we'll not go any further. Correct? Am I right? We'll not go any further. Correct? We'll simply, because we got our answer. But if we are looking for, if we are not looking for 10, if we are looking for any other number like 6, so now we need to traverse both sides. We need to traverse both sides. So now our answer will be depend on these two childs. Our answer will depend on left and right. Correct. So now, now, like, if we are looking for 9, if we are looking for 9, so now 9 will be matched here. So it will not go on further. Once we find out that answer, we will not go deeper. But we need to check for the left side also, right? We need to check for the left side also. So that's why line number 182 is doing that part. Where once you are starting traversing, you are traversing both sides, left and right. So at the line number 182 is giving you both directions results. Yes, or result from left subtree and right subtree. Correct, because in the tree you only traverse in this way, left side or right side. Correct. So where is find method? Okay, so find method is this one. I think we can change the name. This is the only find method, guys. We can change the name. Yeah. So this is our find method. We are just calling the same method. I understood. I corrected it, Hariharan. Find key is written. Yes, I corrected it. It's a find method only. Okay, guys. Are we good now? Or still you guys have any doubt? Why find is not taking any attribute? Oh yeah, you're right. We should take some attributes here also. So it would be taking two things, right? So first is which the key which we are looking, and second would be root. Yeah, or node. We can do that node, and we can remove it from here, right? And by default, when we are calling the find, we can do like this. Okay, find this dot root, comma 11, whatever key we are looking, right? Yeah. It's not taking 11. Why? Oh, we are inside the object. Oh, okay. We are inside the object. So we can do from here. Correct. We can call the method from here. Tree dot find and wait. Tree dot find and let's pass our tree at the end. Let's just pass our tree, the whole tree there, comma 11. This will work in that way. Okay, guys. We can correct the function calling those things. We can correct it. But the main thing is the logic part. Did you guys understood that part? Any doubt on that? Hariharan, Likhit, Joseph, Ekta. Can we call the find function from inside the function without this dot find? No. We have to use this dot find for calling the function. If we want to call the function inside a class, we have to use the this dot function, this dot find, and then we can call it. Okay. I mean, in line number 188, 189, 188, 189. Okay, do one thing, guys. Let's take these function outside. Okay, then it will make more sense to you guys. I think you guys are confused with the coding part of it. Let me move these function outside. Okay, and now what we'll do? These functions are outside right now. Yeah. So now what is this error? Okay, so we need to put the name here, function. Okay, so now let's remove the coding confusion for you guys. Okay, now let's find the tree here. Okay, we are passing the tree, passing the key here. Yeah, so key have, now let's see left and right. Yeah, okay. What about value? Okay, so this should be value. Yeah, same goes here as well. Correct. Are we good now, guys? Are we good now? Yeah. You guys were confused. I can understand with the because we are writing in the class and then put that function there. Sure. Are we good now, guys? So let's move into the next question. Any other doubt, guys, before moving into the next question? Okay. So now we are good. So anyone tried the zigzag problem? Anyone tried the zigzag problem? It was this problem, right? This is the binary tree or queue? Yeah, this was the problem, right? Given a binary tree, your task is to print tree nodes in zigzag manner. Okay, so see, the question is like this, guys. 1, 2, 3, right? Then we have 4, then we have 5, then we have 6, then we have 7. Correct, guys? That was the binary tree which has been provided to us. And you know, they are asking us to print this tree in zigzag manner. And you know that how zigzag work? Zigzag work like this. You know, this is the direction which zigzag follows. So first it goes from left to right. then it goes from right to left, then again left to right, then right to left. So according to this flow, our answer would be looking like this: 1 comma 3 comma 2, and then we have to start from left side: 4 5 6 comma 7. This could be our answer. Small groups. Everyone understood the question, guys? We got one binary tree and we need to print it in a zigzag manner. Everyone understood? Anyone wants me to explain it again? Joseph, Arad, anyone? Are we good there with the question part? Okay. Okay, guys. So now we are good here. Okay. So now, okay, let's observe some of the things. So, we have to definitely traverse the tree, right? We have to traverse the tree. So now for traversing, there are two ways. One is the BFS and second one is the DFS. And I'm sure everyone can see that the traversing which is happening here, which is looking very much close to BFS. Agree, guys? Which is looking very much close to BFS. Correct? But in the BFS, if you remember, every time we go from the left to right, right? In the BFS, how we do the things? We do like this. Like this is our Q, and we first insert 1. Correct? First we insert the root, then we take this element out. Correct? And then we push left and right sides of it. 2 comma 3, right? Then we take 2 out of it, and then we push the child of it like 4 comma 5, correct? And then we push the 6 comma 7 after removing the 3, right? So that's how the BFS works, correct? But here you can see every time BFS is working in the, in the from the left to right, every time it is just pushing things into left to right, correct? But in what we need to do, alternate. We need to do alternate. First we need to go left to right, then we need to go right to left, then we again need to go left to right. So what we'll do, guys, we'll take one flag here because we need to do alternative. So once we will cross one label, we will just convert the value of flag. So like the flag value would be left to right, left to right. This is the flag, and the value would be true. So like before iterating, we'll keep this flag as a true. So once we traverse the first label, like this is the first label, right? First we traverse this label. After that, we will change this value to false. So it means we have to traverse now from the right side. Again, we'll change this value after this label. Correct? Are we good with that, guys? Understood? Okay. Now you guys tell me, in the last class, I told you that how can we understand once our label is like ending? How can we understand when we are going to change our label? Correct? No, not that, Suraj. How can we understand when we are going to change our label? Right now, our label is 1. Right now, how we will be knowing that 2 is coming into the label 2, or these elements are coming in label 3? How we will be knowing that? Right? Yes, correct. So see, if you guys remember, I'm not sure you guys have remembered that or not, but we have taken one size variable, right? Which was telling us the Q length. Correct? Now getting something? Now getting some ideas? We will traverse, yes, in BFS, first traversing will go like this: Q dot length greater than 0. जब तक Q में, whenever, like till Q has any element, continuously run that. And then we'll take the size variable here, and which will tell us the Q dot length right now. At what label Q dot length is what? And then we'll run one while of for loop anything, and we'll do size, and then we'll do the size minus minus 1 minus minus. So guys, this particular loop will continuously run for that label, and once this while loop is ending, then we will get to know that our label is changing. Like if I take one variable outside, label is equal to 0, we can simply do label plus plus. Correct, guys? With this way only we can understand where we are right now on that label. Correct, guys? Anyone wants me to explain this thing again from the last class? Anyone wants me to explain it again? You can see, guys, very simple. Let me just quickly rephrase it. Whatever the coding I've written, let me do it. So see, first time root would be 1. Correct? So queue size would be 1. Am I right, guys? Queue size would be 1. And then we will run this loop only one time. Correct? And inside this loop, we'll push their child, and inside this loop, what we'll do? We'll remove this element and push left or right. So we'll push left or right, which will be 2, 3. And then we'll come out of this while loop, and level plus plus level will become 1. Now we are going for level 1. Correct? Now again, size is 2. You can see 2, 3. So this loop will run time 2 times. Once this loop is ending, again, level will become 3. And now our elements are 4. In this particular two time iterations, 4 elements has been inserted. Correct? So that's how we will be able to identify the labels. Are we good with the labels now? Getting it? Yeah. No. Suraj has not understood properly. So which part? Where you got stuck? Okay. So let me tell you again. No problem. So Suraj, have you understood the first part? When we have 1 here and the size, like, have you understood the first iteration? The while size, yeah. So see, Suraj, the inside code is this one, q dot shift. So this will delete that element. And then if I'm not writing the if, so I'm just simply writing q dot push node dot left and q dot push node dot right. And this will only happen when if node dot left exists or if node dot right exists. Correct? This is happening inside the while loop. Okay, Suraj? Got it? No, Joseph, we didn't get the answer. I'm not saying we got the answer till now. We have not got the answer. I'm just telling you the traversing part. Till now, we have understood the labels things. Suraj, now you got it? Or still you have confused a little bit? Got it. Okay. So now, guys, we have understood 2 things here. First, we can easily traverse the labels and we can easily identify the elements. Like in this while loop, we can easily look for our elements. Now there is the one thing, which is at one time we need to go from left to right. Like in this while loop, let me just like write this while loop or for loop, anything. In this while loop, you can understand, guys, in this while loop, you are just traversing from the whatever elements are coming from the queue, right? So let me see. So first 2 and then 3. So first time 2 will come, then 3 will come. Correct? That will happen. Same for 4, 5, 6, 7. First time 4 will come, second time 5 will come, third time 6 will come, and fourth time 7 will come. But now, guys, we need to think something here. So, see, however we are taking the elements from the queue, we cannot change that. Whatever way we are taking the elements from queue, we cannot change that. But what we will do, like where we are keeping our answer. So what we'll do, we'll take one array. For our answer, we'll take one array. And in this array, we can define the way we store our answer. In this array, we will define the way we store our answer. So see, guys, what we'll do for the same example, same examples, if I'm just simply like taking one stack here. So first time I'm traversing left to right. So I will just insert 1 here because left to right. Second time I'm inserting 2, 3, traversing 2, 3. But I need some way to take my answer as a 3 comma 2 from the right side. Correct? Same for 4 5 comma 6. I will do the 4 5 comma 6. But if there are more elements like this, there would be 8 9, then 10 11, like that, 4 12 13. So this time we should put our answer like this: 13 12 11 10. And you can, so guys, you're seeing the flow, that we are going to, while we are saving our answer, while we are saving this value in an answer, we just need to save it from the back side. When once we are going for the right to left, at that time we just need to save our values from the right side. And and the in the left to right, we just need to save our value from the left side, from the starting index. Okay, let me show you what I'm saying. Okay, so just simply take it as a for loop. Okay, for I is equal to 0, I less than size, I plus plus. Okay, and this is our answer array. So what we'll do, guys, first we'll simply take our node from the q dot shift. Correct, we have taken it out our node. Now we'll check if left to right. If it is true, it means we need to traverse from the left side. If this is true, guys, we just need to simply store our answer at I index only, node dot value. So see, at the 0th index, because the size is 1, so I would be 0. So answer 0 is equal to 1. Correct? That would be our answer. Right? Now let's look for, and after this loop, after this for loop, we will make left to right as false. Left to right as false. Correct? So now second time, when q has 2 comma 3, now size would be 2. Now I'm talking about the second level, guys. Now I'm talking about this level where we need to go from right side, not from the left side. So in this case, we will come to else part of it. We'll come to else part of it. And in this else part, we just need to smartly store our answer. And that would be answer size minus I minus 1 is equal to node minus 12. We will store it from the back side. So size is 2 minus I is 0 minus 1 will give us the first index. And then when it is I is equal to 0. When I is equal to 1, it will give us 2 minus 1 minus 1, which is equal to 0. You can see now we are storing all the, so here 2 will be stored and here 3 will be stored. And our array will look like this, 3 comma 2. That's what, this is the smart way we can store our answer in the array. Now let's look for 4 comma 5 comma 6 7. This one 4 comma 5 comma 6 7, because this time 4 comma 5 comma 6 7, this time it will go into this part because left to right is true. So at 0th index 4 will come, at 1 index 5 will come, second index 6 will come, fourth index 7 will come. Now let's look for last one, 8 9 10 11 12 13. This is the last level. All of the elements are here, 11 10 11 12 and 13. So what would be the size here? 1 2 3 4 5 6. So size would be 6 here, guys. So now you can see size 6 minus 0 minus 1 when I is equal to 0. So it will give us the fifth position. So at fifth position, we will keep the 8. So fifth position, 8 will come. Then I is equal to 1. So it will be 6 minus 1 minus 1. It will be 4. So at fourth position, 9 will come. You can see this way we are going to store our answer from the back side. Understood, guys? Okay, so Ekta is saying if left to right is equal to true, then we will use shift. And if not left to right, we can use pop. But Ekta, we are using Q. In Q, we do not have pop. So in one case, we will take from front, else we will take from back. Yes. Yeah, see, if you are simply talking about the array, in that way, it might work, your way. But yes, this is the easy way if we are going with the Q. If we are going with the Q method. Yes, Ekta, then I think it could work. Let's look for that. Let's look for that. So if we have 8, 9, 10, 11, 12, 13, and if you do the pop, so yeah, 13 will come, then 12, yes. Yes, that will work. That will work, Ekta. Can we do this BFS approach rather than size approach? This is the BFS approach only, Joseph. Size approach is just for giving us label. This is the BFS approach only, In the BFS, what's the BFS approach? BFS approach is push the element from the back into the queue and uh, take it out from the front. That's what we are doing. You can see q dot shift every time we are doing. You can see in this line. And then there would be one more, like after this, there would be one after this else part, there would be one more thing. If node dot left, this is the BFS, right? If node dot left, q dot push node dot left. If node dot right, q dot push node dot right. This was the BFS only, right? Yeah. Did you guys understood the logic part first? Anyone has any doubt in the logic part? Suraj, what about you? Arad, is still facing electricity problem, or today your internet is good? Kind of confused with which part? You understood the question first? Arad, you understood the question first? Yeah. So now under you, after understanding the question, have you watched the, okay, I remember you have not watched the previous, you have watched the previous recordings because you were not in the last class. Have you understood the Q part? Yeah. So you have understood the BFS part, right? And you have also seen that in BFS, every time we are taking from left to right, every time we are taking from the left to right. Correct? Every time we are traversing our element in BFS from left to right, from left to right. Correct? That's what we are still doing it. That's what we are still doing it. We are traversing still from the left to right. So you can see 8, 9, 10. You can see every time we are doing Q dot shift. So 8 is coming, then 9 is coming, then 10 is coming. But just little twist. Just little twist. And that twist is in storing your answer. In storing your answer. So what I did, I have taken one array for that, for storing my answer. So first 8 will come. Okay. So if my, so what I'm doing, because our question was saying we need to traverse it in a zigzag pattern, in zigzag patterns. So in zigzag pattern, what happened, at one level it goes left to right, and another level it goes from, at another level it goes into right to left. So at one level where it has to go left to right, we do not need to do anything. You can see when it is going left to right, I'm not doing any smart thing. I'm just simply whatever index I'm traversing, I'm just keeping it as my answer. In that index, I'm keeping my answer. But when we are traversing right to left, we need to insert from back side. We need to insert from back side. If we have an array of 5 size, correct? If we have an array 5 size, like this is the 5 positions, 3, 4, 5, correct? And if we have like 5 numbers, 11, 12, 14, 15, if we want to keep them from the if you want to keep them from the left to right, so they will be looking like this: 10, 11, 12, 14, 15. This is left to right. Okay, Arad? This is left to right. And now if you want to keep the same numbers right to left, so this number will look like this: 10, 11, 12, 14, 15. Did you understood these two things? Arad, did you understood these two things? So we can see the entire approach for the code. Sure. But let me just cover it for him. So see, Arad, what I'm doing for storing the same number, when I have to go to left to right, I'm just keeping at the same index: 0, 1, 2, 3, 4. So I'm just keeping them at the same index, right? This is the code. I'm keeping at the same index. Now you understood left to right scenario, understood? Arad, left to right. Now let's go for right to left. So for right to left, I need to keep this element at the last index, which is this. So what I did, I have taken whole size of array, which was 5 minus index value. So right now I'm just traversing from 0. So 0 minus 1. So it will give me 4. So here it is size, Here it is I, here it is 1. So you can second time when I is equal to 0, it will give me 4. So at the fourth position, I will store 10 here. Then I is equal to 1. I'm going for 5 minus 1 minus 1, which will give me 3. And same will go for further. Now you understood? Yeah. Now you good? Now are we good, Arad? Okay, now let me read the Ekta's question. Can you please zoom out a little so we can see the entire approach for the code? Sure, let me do zoom out. Okay, 1 minute. We are just changing the index from which we start taking the element in both the scenarios. One is start from 0, another case. Yes, that's right. That's right. We are pushing array into the stack. Yes, at the end, we can push these arrays, answers into stack. Let me show you the code. We have the code for that. I have the code for that. Zigzag. Yeah, this is the code, guys. There are two methods actually. The in the slides they have given with the stack also, but in they are using two stacks. With the help of two stacks also we can do that. But yeah, you can see here. So I have taken current label and answer. This is the final answer. You can see. This is the final answer or final stack which I am going to return as my answer. You can see at the end I'm returning that only. And you can see I'm starting. I first pushed my root, taking one flag left to right. Then this is the first while loop. Then I'm taking size there, correct? And this is my for loop. And you can see after this for loop is completing, I'm just changing the value of left to right. First time it is true, it will become false then. Then next time it will become true. The next time it will become false. So negation will just make true to false, false to true, false to true, true to false. That's what negation does. And then you can see every time I'm just pushing my label answer. So that's what your answer. That's what your answer to your question, Joseph. At the end, we are pushing this label answer in answer, and you can see inside the code whatever I'm telling you. Current label 0, current label dot shift. This is the queue, and then left to right, simply keeping it as a same index. If not, then size minus I minus 1, and then we are checking if it has left child, push it into the queue. If it has right child, push it into the queue. This is simple BFS. This line is simple BFS. This is all BFS. It just these four lines are new here. These four lines and these two lines. These two lines are new. Otherwise, everything is BFS. Understood, everyone? Joseph, you got answer for your question? We are pushing array into stack. Yes, we are doing it, and then we are returning that as my answer. Okay. So anyone wants to see the code? So let me just zoom. Yeah, you guys can see this code now. Yeah, it starts from here and then it goes. Let me just. Okay, so you can't. You guys can't see that. Yeah, this would be better view. Okay. And I think here, if I can zoom in or zoom out, yeah. So zoom in if I will do. So see, this will look like this. Okay. I think yeah, you guys have understood, right? The logically you guys have understood, right? Whole BFS part, but we just need to while we are storing our answer, that's where we just take care of this zigzag part. Okay. Are we good now? Can we move into the next one, guys? Before moving, anyone has any questions? Anyone has not understood the logic or code? Okay, we are good, right? Suraj, Hariharan, you guys are not responding. Understood. Okay. What about Suraj? Suraj, are you still in the call? I think he has left or something happened. Okay. Okay. So next question is, guys, the insertion on binary tree and deletion in binary tree. Okay. Now that's the next part, which we are going to look into that. Let me see if I have the code for that or not. Yeah, insert delete. Oh, okay. Yeah. I'm just remembering. Okay. So now let's see. Okay, guys, let's start from insertion part. Okay. So see, guys, in the binary tree, they have not told any, like, because this is a tree, right? Tree which are at the end objects, right? So let me show you. So first understand how the tree looks like. See, if I want to create a tree like this, where this is the first node, this is this, and this is this. If I want to create a tree like this, you know what I need to do? I just because these all of these elements are a node, right? Are node. So what? How will they look like? They will look like this. So first we'll create a one class. That class will be tree node, tree node. Then here we will be having one constructor for them, which will be taking a value, comma left, comma right, right? Which would be taking some value like this dot val is equal to val, right? I think we do not need left and right here. And this dot left is equal to null. Oh, no, no, no. We can take it. Yeah, we can take it. Left, comma, right. And we can provide the default values like them. I think it will be on the top. Yeah, you can see these things. We can take left and right, but yeah, I think do not need it. So left and right. So this will be our node. Let's copy it from here. And let's put it into here. Let's see if it works here. Yeah. And how can we create a new object out of it? It will be like this. Let node is equal to new node, and one is 5. And if I now look for node, okay, so now you can see this is our tree, right? With only for one node. So this looks like this. 5. Correct, guys? This is our tree. Correct? This is one tree. We just created one node, and that one node can also be a tree for us. So this is simple one tree. Now, what will create? What do we have to do? If we want to make something like this, 5, 4, and 1. If we want to make relation like this, so first we have to create two more nodes, 4, comma 1. So let's create two more nodes. Let's create two more nodes, and we'll give them a name as let. Just use the older one. So this is the which one? 7. Which was 4, comma 1. Sorry. So this is the 4. So I'm just giving them name as a node 4, right? And then we have to create the 1 as well. So node 1. Now we have created three nodes, guys. So node 4, you can see that node 4 is there. If I put node 1 is there. And if I simply put node, so all three nodes are there. So now we just need to make simple relation. So as we can see, the node dot left is equal to this node. So that's what we are going to do that. So node dot left is equal to node 4. Correct? And then node dot right is equal to node 1. Now if I open the node here, guys, you guys can see that. You guys can see that node. This is my root node. Then we have left, which is having key as a 4. It does not have any left and right, so that's why it's coming as a null. And then in the right, we have the node as 1. So that's what similar representation. You can see 5 as my root node, and 4, and you can see they have left and right as a null. This one also has a null. And that's what you can see here as well. This is my root node 5. Left of it is 4. Fourth left is null. Fourth right is null. Fourth the right node is 1. That left is null. That right is null. So that's what we can see here. So that's how we can only do the insertion here. Okay, guys, that's the only way, because it binary tree is not providing us any specific constraint. So we can do in this way only. Wherever we want to add it, this depends on us. where we want to add it, because there is no restrictions. We can add anywhere. Are we good now, guys? In the binary tree, there is no restriction on while insertion. We can insert anywhere. Yes. Yes. Once we will talk about the binary search tree, insertion will make sense there. But simple insertion in binary tree, it just depends on us where we want to add the node. But when we'll talk about binary search tree, they have given some condition for that. Their insertion will matter, but here insertion will not matter. Yes, yes, Ekta, please tell. What is your quick question? In meanwhile, everyone understood the insertion part is very easy, right? Simple adding a node. Yeah, Ekta. Oh, you just, I think, cancelled it.
So am I audible?
Oh, yes, you are. I thought you cancelled it. Yes, you are.
That since insertion is like not very logical in normal binary trees, so can we like not pay much attention to it, because as we saw that in trees, when it comes to trees, we are only focusing on the some like good functions, such as comparing the symmetrical or same trees, or like finding a key. So like, is it okay if it kind of skip that insertion part? Because I tried understanding it from the code repository, but it was like not very logical. It was just node dot left, node dot right equals to that.
Yes, actually, for the insert, see,
Hello.
if people are asking about the insertion, so they will be definitely we are going to ask for BST, binary search tree. They were not going to ask addition or insertion of it for the binary trees, because in binary tree it does not make much sense. In the binary tree, it means you just need to simply add the nodes anywhere you can add. But in the binary search tree, they have provided some restrictions, and we will talk about it. Okay, but yeah, deletion makes sense here.
Yes, sir.
So
So
that's what we are going to discuss after the insertion.
okay, sir. Okay, sir. So from interview point of view, can we
Yeah,
just like
deletion will make
skip
sense.
the insertion of nodes here? Okay, sir.
See, they will not ask insertion to you. Yeah, and if they are asking you, so you can
That's
simply
what,
tell
sir.
them the way which I told you. Okay.
So like
So now let's jump into the
object,
deletion
then
part.
we can assign node dot dot.
Correct. Correct. Yes. So and everyone good, right? Joseph, Hariharan, you guys understood, right? Insertion is very simple, right? The similar way we create the nodes in linked list, right? That's same here. BST your Git profile and got missed about how missed it. Not a problem. We have the recording for that, and I will continuously repeat it wherever I missed it. Wherever actually it like it's needed, I will just simply repeat it. Okay. Now let's go for the deletion part. Let's go for the deletion part. I'm like so whatever I remember, I'm also like getting some ideas about the deletion. But let's see what like, till what I remember about the deletion, I will just discuss about it. Then we will see if I am missing anywhere in the deletion, because there could be multiple scenarios. So that's what we will see into that. Okay. So now see, guys, for the deletion, let's look for the same node. 1, 4, 5, 6, 7, and then 8. Okay. So see, guys, first let's understand with the help of tree what we does. In the tree, we simply, you know that we just simply traverse it, correct? And we simply wants to find out some elements from the tree, correct? So the complexity of a tree depends on its height. How longer your tree is, that much you need to do, that much you need to that much traversal, or that much depth you have to go there, correct? In the binary trees, if we talk about the binary tree, at the label side we can simply add two nodes, right? But if we want to talk about the complexity of a tree, it always depends on the maximum height. So right, so whenever we are deleting any element, whenever we are deleting any elements from the binary tree, we always try to delete it from the last. We always try to delete it from the last, or from the last, like whatever nodes is increasing the height of a tree, we always try to delete the last node, that delete that last node. Like if we talk about, in this example, if you want to delete 5, if you want to delete a 5, correct, so we will simply delete the 5, delete the element 5 from here, and we'll replace it with 8. Why we are replacing with 8? Because once we'll replace with 8, it will reduce the height of a tree. You see, this will become 4, this will become 8, this will become 6, and this will become 7. You can see now height has reduced. Correct? Because while we are traversing it, you know that if you talk about the recursion or in the queue, we traverse on the level side, on the level, we traverse on the level, right? And if we want to go, if already have extra labels, so we have to traverse it again. So that's why, guys, whenever any node we are deleting, we always replace it with the last node, or the node which is increasing the height. Like if we talk about this example, 1, 2, 3, 4, 5, 6, and 7. If this is the scenario, and if you want to delete a 3 or like 2, so what we'll do, guys, we will delete this 2 and we'll replace it with 7, the last element. This is the thing you need to remember. This is the thing you need to remember for the binary tree. First, first thing is we have to you know delete the last node, and that last node is could be in two scenarios. The last node could be in this scenario as well, which is increasing the height, and if there is any node which is not increasing the height, so that whatever the last node is, that you need to remove it. That node will be replaced. So see, after deleting the 2, it will look like this: 1, 7, 3, 4, 5, 6. That is what you need to do, guys, in the delete scenarios for the binary trees. Yes, we always replace, not replace. We remove the last node, and then we go for the then replace the last node value with the previous one. And why not with either left or right of the node to be deleted? For this case, why not with either left or right? So see, from the left side, if we'll delete, so see, guys, if you talk about this part, so in the like mostly if you're talking about the in order, so most of the time, if you remember, left and right, always left come first and then right come. Like if we talk about in order or pre-order or post-order, so we always, you remember, node comes anywhere, but left come first, then come the right. Correct? So that's why whatever the last is coming, that's why we always prefer to remove the last one. Correct? So it will because if once we will remove it, it will just reduce our one of the iterations from here. Correct? Otherwise it will go for left. If we will remove the left from here, this 6, it will still go for this iteration, right? And then it will be finding out the null, then it will not go there, then it will go for the backside. So that's why we mostly go for the last node, and then we remove it from there. And in some sense, in somewhere they are writing also, we have to remove in order successor. Like if we are doing the in order of it, so whatever is coming at the last, in the BST also, if we talk about the binary search tree, there also we do that. In the last node, we when we are trying to replace it, we tried it with the in order successor. Correct? So that's what the logic is here because of the left and right. But I can go a little bit more deeper into that. Little bit go. I can read little bit more about it and then come back on the Monday to answer it properly. I'm also not fully sure, but whatever ideas I got, why they are doing it. So that's what I shared with you guys. But yeah, I can look into this one. I can just find out little bit more places why we are going for the right side only, not for the left side. Okay, there might be, definitely there would be reason. Okay, okay, Vishal. So I will just look for that one. Last note from left or right? Last note from the right side. Joseph, from the right side. So we have to look for the right side. Right element will get delete first then. Yes, that's what the right element we have to delete the right element first. Okay. So I will look for the reason. I'm right now not fully sure about the reason. Whatever I thought, I shared with you guys, but I will look for the proper reason. Whatever other people are saying, I tried to find it out, but I didn't get proper answer. So I will look for that, and then we will, uh, uh, talk. We will definitely talk about it. I will write it in my notes. We will definitely talk about it in my next class as well. Insertion from left and deletion from right, sir. Insertion from left and deletion from right. Mm, Insertion depends on our choice, Arad, in the binary tree. Insertion we can do anywhere on the left as well as the right. But I think deletion logic is little bit depends on traversal. Deletion, the reasoning for deletion is little bit related with traversal. So that's what I will read about it and I will tell you. But I'm not sure about what you mean by this, Arad, insertion from left and deletion from right. We're only talking about the deletion here. Insertion in binary tree, it's your choice. You can do it on the left, right, anywhere. Understood, Arad? Okay. So now let's talk about, guys, how we will write the code for it. How we'll write the code for it. Okay. So now you can understand if we take the any of the tree here. Let's take any of the tree here. 1, 7. Oh no, this was 2, right? Let's take the older example. 2, 3, 4, 5, 6, and 7. Correct? If this is the tree, okay, guys. So and if you want to delete 2, if you want to delete 2, so what I told you, first replace this 2 with the last node here, with the last node, and you can see whatever order you will traverse, always 7 will be the last node. Whatever order you traverse, 7 will always be the last node. Correct? So now, one minute, guys. So now, what we'll do, what we need to do, we need to replace this 7 with this 2, and then we need to delete this thing. We need to delete this node. Am I right, guys? That I told you. Replace the last node with the delete node, and then remove the last node. Are we good with these two lines? Yes. So see, guys, what we need to do in this whole tree, first we need to identify which key we need to delete. Which key we need to delete. And then the second pointer should be here at the last node. Am I right? Am I right? The second pointer should be at the last node. Correct? So once we reach to the last node, after that, what we need to do? We need to simply, wherever right now this pointer is delete key, I can say this is the delete key pointer. So wherever my this pointer is, I will simply do this thing. Delete key dot data is equal to last node dot data. If I will do this, guys, our tree will look like this now. 1, 7, 4, 5, 3, 6, and 7. Am I right, guys? After running this line, see, first we'll traverse whole tree. First we'll traverse whole tree with the same way. Right? If you want to go with the recursion, so simply left and right, left and right, left and right. And wherever we find out the key, I will keep that pointer there only. Delete key pointer at that place, and then at the last I will point out the last pointer, last node. Correct, guys? And then we'll do delete key dot data, will update the data of this key, will make the last node of data. Will look like this? 1, 7, 3, 4, 5, 6, 7. Everyone agree with that? After doing that, Joseph, everyone understood this thing? Yeah. So see guys, now the next step for us is to delete this node. To delete this node. Correct? Now the next pointer for us is to delete this node, which is the last node. Correct? Which is the last node. So deleting this node, what we need to do? See, if this node, if this is the last node, for deleting this node, somehow we need to reach to the parent node. Somehow we need to reach to the parent node. Yes, we have to go to one step back to its parent, and then yes, and then do the parent dot write is equal to null, as Ekta is saying. Correct, guys? That's what we need to do. We have to go to the parent node, and then from there we need to do the parent node dot null. Correct? So let me show you the let me guys first show you this part of code, and then we'll talk about the second part of code. Okay? So let me first show you the first part of code. Yeah, insert delete. Yeah, this was the code, right? Let me zoom it out. Yeah, so you can see. So this is the first, like this is the first scenario, guys. This is the first scenario. If I only have one node, if I only have one node, like this, if I only have one node, like this, 5, and you want to delete this node only, you want to delete this node only. So what I will check, if this node does not have any right, if no, this node does not have any right left, so just simply make this node as a null. Correct? So that's what happening in the code also. You can see if root dot left, root dot right is equal to null, it means we only have one element, and that is our root. And if that root key is equal to key, we'll simply make our root as null. Otherwise, we'll simply return it. Did you guys understood this thing? This thing is very easy, right? If we have only one node and if we want to delete that one, we'll simply make that node as a null. That one is deleted. Correct? Now let's go for the further scenarios. So for that, you can see I'm taking one queue for traversing, and then you can see q dot push is we are pushing our root, and then I've taken two variables, temp and key node. Temp will point out the last node, and key node would be the node where key node would be this one, guys. Yeah, so this last node I'm taking it as a temp, and this node I'm taking as a, what was the name I'm taking as a reference? Key node. I'm taking it as a key node. Okay, so now let's see how the code is writing. So I'm again see from the queue, I'm taking first element. So first time I will take the one. I will check it. Is it matching the key? No, it's not. I will not update my key node. I will not update my delete key. Okay, then I will push 2, 3. You can see if it has left, push it in the queue. If it has right, simple BFS code. Okay, continuously doing it, like we are trying to delete 2, right? So first time we'll get the 2, so we'll simply keep our key node at that place. So this pointer will be at this place. Correct? And then again traversing. Why we are traversing whole? Because we want to find out the last node, and at the last node we will get it, this one, where we'll get a temp. Understood this part of code, guys? First part of code, everyone understood? Are we good with that? Okay, now let's go for the next one. Now let's go for the next one. So see guys, we just need to traverse it again. We just need to traverse it again. See guys, we will not update this tree. We will not update this tree. We'll keep the keynote in this place. We'll not update this one. So now we'll traverse it again. And while traversing, I will just check wherever in this tree my last node matches. Like, see this last node, this leaf node can be at anywhere, right? It could be somebody's right, it could be somebody's left, right? It could be somebody's left, it could be somebody's right as well. So just we need to check for any node I got, if that node's right matching with the last node, or if that node's left matching with the last node. If that's what, make that left as null or make that right as null. Understood, guys? What we are doing, we are again traversing the same tree, but this time we are looking for the temp node, which is our last node. And how we are looking it? Because that temp node can be somebody's left child or can be somebody's right child. Did you understood this line? The last line I'm telling you. That last node, that the last leaf node can be somebody's left child, can be somebody's right child. Did you guys understood this line? Because this line is important. Because while traversing every node, we are going to check this thing only. If somebody's left is matching with this temp, or if somebody's right is matching with this node, just make that left as a null or make that right as a null. That's what we are going to do in the code also. So if I show you you can see after this loop, you can see I'm saying that if key node is not null, keep the temp key value right now, because the temp key, it means 7. This one we have to replace it with 2. So that's why I'm taking it as it here. And again, I'm calling delete deepest and I'm passing whole tree and temp. So if you can see, till now I have not changed my root tree. I have not changed this value. So I'm passing my tree and temp value. Temp will be 7. This temp will be 7. The last node. And you can see in the delete deepest what is happening. Let me show in the delete deepest. You can say again I started the traversing here. Q dot push, and then again doing the same thing, taking the first element, and then I'm checking if that first element is the delete node, make that as a null. If not, go for the right side. If temp dot right is equal to delete node, make that as a null. If not, look for the left side. That's what I'm doing. Correct, guys? If somebody's right is the delete node, make that right as a null. If somebody's left is the delete node, make that left as a null. Understood? Guys, I'm not sure you guys have understood this thing or not, because you guys are not responding. So what I'm saying, I'm just start traversing from this node. I'm just checking, is this left is equal to the last node? Last node is 7. Is this left equal to 7? No. Okay, that's fine. Look for right. Is this right is equal to 7? No. Okay. Go for again left. 4 is equal to 7? No. Is 2's left is equal to 4? No. Is 2's left? No. 3's left, 3 7? Yes. 3 7 is. So I will simply make this 3's right to null. That's what happening in the code, guys. Everyone understood now or not? This part. Understood, right? So that's what happening in the code also. You can see if temp right is not equal to null, then I'm checking if temp right is equal to delete node. If yes, make the temp right as null and then simply return it from here. If not, look for the temp dot left. If not, push it into the queue. Understood, guys? But there is one more way. You can see we are traversing 2 times. We are traversing 2 times. But is there any way so we can reduce our traversing 2 times one? Delete node easily point to 7. Delete node, no, not delete. Delete node is the temp one. Temp one. Joseph, I am passing the temp node, which is the last node. You can see in the delete method, you can see in the delete deepest, I am passing the temp node, not the delete node. You can see, or key node. I'm not passing the key node. I'm passing the last node. Understood? We are looking for that one. Delete node initially, finally, everywhere it is pointing to 7 only. Delete node is an internal variable. Delete node is the variable which delete deepest is taking. It's not coming from the back. It's not coming from the previous function. It's a new variable which is pointing out to temp only. It is pointing out to temp only. So temp, the last node we are sending only. Okay. Okay, guys. So, so there is one more way. That's what I written it down. The FEC and delete. Temp points to 7. Yes, you can see in the here. This is the temp. This is the temp, which is pointing to 7. And temp always pointing to this only. I didn't understand the initially mean. First we done the first traversal, temp come to 7. That because that's the last node. Right, Joseph? First we do the first traversal, temp come to 7. Okay, you want to see the code? Okay. You see, we have taken two variables, temp and keynote. Keynote is equal to temp. Correct. So this is the delete node, which we want to delete. Correct. Then we are traversing whole trees, and then at the temp, at the end temp will be pointing out to last node, which is 7, right? And then we are passing, because we want to delete that 7, so we are passing root and then temp. We are passing it here. And once the here it will be deleted in this function. And once that is deleted, we will update our keynote dot key, the value of keynote to the deleted node. Got it? Then in above delete function, you mean in the delete or delete deepest? Which one? In the delete deepest, there is any temp or not? In delete deepest, oh, there are, yeah. Yeah, in both places, temp will always change. Yes, in both places, temp will change. Temp is taking value from Q. Guys, temp is taking value from Q. It is always changing. Both places. You see, temp is always taking the value from Q. Yeah. So now, guys, let's think about some make this code little bit better. Why we are traversing two times? Why we are traversing two times? Because why we are traversing two times, guys. Anyone wants to give any idea? This is the route. Is there any way without traversing two times? See, what is the requirement here? First, the delete node, which is this one, or key node, which you want to delete. And second one is temp. And third one is the parent. Right, guys? These are the 3 pointers we need to take. These are, sorry, not 3 pointers. These are the three things which we require. Correct? These are the three things. So in one traversal only, can we do that or not? In one traversal, can we do that or not? I just thought about this solution. Yes, we can do. When we are at the label, at that time, we will be. But there is one more thought. There is one more thought you need to have, that how will you find out the node which you are deleting, it is on the left side or at the right side? It is at the left side or at the right side? How will you know that? How will you know that you need to delete the node at the left side? Because see, this could be one more. See, in the equal scenario, it's very clear, right? Both of the nodes has three parents. So you can understood that. You can simply say that parent dot right is equal to 7. If parent dot right is equal to 7, delete that. But if this is the scenario, 6. Now will that logic will work? Now will that logic will work? Parent dot right. You are saying parent dot right. That's not correct. Right, guys? See, in this case, this will be parent, this would be our temp, and this would be our root, and this would be our keynote. And earlier logic was in this case, we were thinking that parent dot right, if parent dot right is equal to temp, We'll simply delete it. Parent dot right is equal to null. Correct? We'll do that. But here, in this case, it will not work. Can we add a flag for that? Yeah, that's what I'm thinking also. Or wait. Hmm. 1 minute. Let's think about it. I think with one pointer we can do that, right? Because see, I'm just thinking about right now it is. Earlier I was thinking like it can't possible, but right now I can think if we will put one more condition here. If parent dot left is equal to temp, then parent dot left is equal to null. Right? We can put the second if condition. What do you guys say? And we will first, but here, no. Yes. I think it will work. Right? What do you guys say? Will it work or not? See, we just need to put two conditions there. Parent dot right is equal to temp. Parent dot right is equal to parent dot left is equal to temp. Whatever is matching, we can just delete that one. Agree? Because at the end, we need to delete the right side. Are you guys getting it or not? Okay. So see, guys, what I was saying, if we can take one pointer here as a parent, which will be telling us the last node's parent, so we do not need to traverse whole tree again. At the end, we can just apply these two conditions. If parent dot right is equal to temp, so if right matches with temp, we'll just simply we'll remove that. Correct. If left matches with temp, we'll simply remove the left one. Both scenario will work. Got it? Correct, guys? Both scenarios will work there. Is there any scenario which is left? That's what I'm thinking right now. Let's think about it, guys. Okay, so we'll think about it if any scenarios comes. But what I did in the code, I have taken both parent left, parent right. Two parents I have taken. In my code, I have taken two parents. But right now I'm thinking, I think with the one parent also it could work. Just give me 1 minute, guys. Let me think. So for 2, 3, parent would be 1, right? For 4, 5, 6, 7, for 4, 5, parent would be 2. For 6, 7, parent would be 3, right? And then the parent dot left, parent dot right. Okay, what about this scenario? 1 minute. Let's talk about if we are moving to here. Yeah, because this is now the last node, right? What will happen here in this scenario? So now, if we talk about yeah, so this is the one, and yeah, so for 2, 3, parent would be 1, right? For 4, 5, parent would be 2, and for 6, 2, parent would be 3, and for 8, parent would be 4. Yeah, it's still working, right? Parent would be 4. and that would be our last node, and parent would be here, and that would be our last node. Correct? And then we can simply check for parent dot left matches. Yeah, guys, I think it will work. With one parent, it will work. Are you guys getting it? What I was checking there? Guys, are you guys able to understand what we are talking here right now? Or I can repeat it, no problem. Can you guys just... Okay. So if you guys are able to understand it, confused a bit about which thing, Arat? About which thing? About the see. Okay. I think I made it confused because I was also a little bit confused about the two parents and one parent. So let me now read it. Let me do it again. So one, not a problem. One, what is happening? One, two, three, 4, 5, 6, and 7. So see here, we want to delete 2, right? This is our delete node. And this is our last node. Correct? This is how this is you guys have understood, right? This is you guys have already understood, right? No. That's not complex. Let's now just hear it. Okay, this you guys have already understood. And then what we did for deleting this node, somehow we need to know the parent of it. Somehow we need to know the parent of it. You guys have understood it, right? So for finding out the parent, we have already traversed the one way. We have already seen the first approach where we were just using root again and passing this last node value as a 7. Last node value as a 7. So wherever right or left child's value becomes 7, right, or so we just make that node as a null. We have already seen that first approach. Everyone understood the first approach? Anyone has any doubt with the first approach? Already seen that, right? So now in this way, in this approach, second one, I'm saying no need to traverse it again. Somehow, while traversing first time, when we are trying to find the last node, try to think something so we can also find out the parent at that time only. We can find the parent at that time only. Do not need to go for the second loop, second time actually. We are, see, after traversing whole tree, we are traversing it again. Correct? So that's what in the second approach we are going to do. We are going to take one more pointer as a parent. As a parent. Correct? So first the pointer will be null. Delete node pointer would be null. And then we have our temp as well, or temp or last node, whatever you want to say. Temp as also. All three are passing, all three are right now in starting pointing to null. And then we have one queue, right? Now in the queue, we will first push 1, right? Make our temp as 1, correct? Temp as 1. Now we'll check, is the delete node matching? Because our delete node is delete key is 2. Is it matching with this? No. So we'll remove this one. We will remove this one. Correct? And now we have to look for if it has left or right child. So yes, it has left. It has 2 as the left. So we will push that 2 here. And now we will update the parent. Now we will update the parent. So in the parent, we will first update to 1. Correct? Before inserting. And then we will insert 3 as well. We will insert 3 as well. Now we will update this parent. Now we will update this parent to, yeah, still it is 1, right? Yeah, for 2 and 3, parent is 1. Yes, still it is 1. Okay, now let's take the top element from there again and update temp to 2, the top element from the queue. Correct? Now we will again check, is it matching with the delete node? Yes. So now delete node will also pointing out to 2. Delete node is also pointing out to 2. Now again, child of delete node, which are 4 and 5. And now parent has become 2. Now our parent has become 2. Correct? Now we'll take out 3. Now we'll take out this one, 3. Correct? Now we'll insert 6 and 7. 6 and 7. Now our parent will become 3. Now our parent will become 3. Correct? Now, now we'll start traversing 4. Because it does not have any child, parent will not change. Now our temp will become 4. Correct? Because it does not have any child, so parent will not change. Now we'll go for 5. We'll update the 5 here. Parent will still not change because does not have any child. Now we'll go for 6. Update the 6 here. Now we'll go for 7. Now we'll update the temp to 7. So now you can see temp is pointing out to 7. Parent is pointing out to 3. And delete node is pointing out to 2. And now we can simply replace it. We'll simply check it. If 3 dot, if we will simply check it. If parent dot write is equal to temp dot value, or parent dot write dot value is equal to temp dot value, simply make parent dot write is equal to null. This is the first condition. Second condition would be if parent dot left dot value, because this could be in the left as well, is equal to temp dot value, delete the parent dot left is equal to null. And after doing this, before this also change the value of delete node. So delete node dot key or value, whatever is this, is equal to temp dot value. This is the code, guys. Yeah, it's like previous, but we are doing in one iteration only. And you can see in the code also, I have the code, but you know guys, in that code, I'm using 2 pointers for doing that. You see, I'm taking PR and PL. See, same code, PR and PL, but you can see, but I'm thinking with one pointer also we can do that. So PL is equal to current node, PR is equal to current node. That's what I was thinking, like I should know the parent, it is coming like from the right side or it is coming from the left side. So that's why I've taken PL and PR. And then at the end, you can see I'm just checking PR dot right dot key is equal to current node dot key, or PL dot left dot key is equal to current node dot left dot key. But I think this could happen with one pointer also. This code could happen with one pointer also. I can remove this console. This code, you can see before that, just updating the key node key as well. And current node is here, temp, the temp which I'm talking about. And you can see at the end, PL dot left is equal to null, PR dot right is equal to null. But let me quickly make the change here. I think we can, yeah, you guys can try it. Let me copy this function and give it one more name. Efficient delete one parent with one parent. Just giving you some name different. And thus you need to remove this parent from here. In the same code, this is our parent, right? And now update that parent both times while pushing left, while pushing right. And then at the end, check it from one parent only. Okay? Yeah. And this code should work. We have already seen it. Anywhere you guys stuck? It was easy, right? It was easy. Yeah. So I think these was the two questions from our assignment, guys. Now we can talk about the new topic. Okay, which is BST break. Oh, okay. Oh, we have spent a lot of time today in these two questions. I hope you guys, I hope everyone has understood these two questions, because these two questions was interesting. Okay, so now we can go for break quickly. So right now it's 9:37. So we all can come back at after 15 minutes, which is 9:52. So let's come back at 9:52. Okay. Wait for 2 more minutes, then we'll start. Yeah. Okay, so is everyone back? Can you guys hear me? Thank you, Arad, for confirming. Great. So now, guys, let's talk about our next topic, which is BST. So let me open the slides for that. You guys are able to see my screen? Yes, great. So, guys, the BST, the full form is binary search tree. And same, it is same like BST. It can also have at most two children's, means it can have zero children, one children, two children's, but it has one more special property. One more special property, that whatever node we are right now, whatever node we are standing at right now, it that node value would be the greater than the value of left subtree, greater than the value of left subtree, or and the lesser than the smaller than this, and all the right side of that node, all the elements would be greater or equal than that, would be greater or equal than that. So that's the property which BST provides us. So if we talk about the BST, so if this is our node 4, so all the left side of it would always be smaller. So like 3, 2, 1, like this, right? And all the right side of it be equal or greater. You can see would be equal or greater. So like for the duplicate elements, if there are duplicate elements, they would be going on the right side. Or if we have the greater element, they would be going on right side. Correct? So that's what the BST is. So let me draw it again, guys. Like if I have 8, can you guys hear me? 1 minute. My browser is refreshing. I'm not sure what happened. 1 minute, guys. Actually, my browser is still refreshing. Oh yeah. Oh yeah, I was not able to see your comments. Yes, that's right. Can you guys hear me now? Yeah, now all the comments are coming. It's stuck those things. Yeah, might be some internet problem on my side. Okay, so can you guys hear me and see me? And I'm right now sharing my screen. Can you guys see that everything? Okay, visual. Yeah, great. So yes, as I was explaining about the binary search tree, so I told you it's totally similar like the binary trees. Like the binary trees has properties. The binary trees should always have almost two childrens. Should have always almost two children. Means they can have zero children, they can have one children, they can have two children. Right. So in similar way, binary search tree also follows the same criteria. It can have zero children, one children, and two children. But in binary search tree, we have one more property, one more condition, and that condition is that if we are standing in any of node, so the left side of it should be smaller than this, smaller than this, smaller than the node, and the right side of it, it should be greater than or equal to the node. Right side of it and equal right side of it, it should be greater or equal to the node which where we are standing right now. Okay, I have shown you this example also. As you can see, if this is my node, if I'm talking about this is my node, so you can see all the element in the left side, it is smaller than this. All the elements on right side are greater than this. Right, guys? So that's what the BST is about. Okay, after that I ask you about this question: is this tree is BST or not? You guys tell me. You just see this with the same condition, just try to find out, is this tree is BST or not? So Parag says yes, Vishal says no, Saras says yes. What about others? What about others? Two people are saying yes, one people are saying no. What about others? Joseph, Ankit. Okay, you guys have not seen it. The second one I'm talking about, this one. Is this tree is BST or not? Binary search tree. Hariharan says no. Arad also says no. Now everyone is saying no. So Joseph and Parag is saying yes. Yes, that's right. Hariharan has catched it. So any of node, if I'm talking about this node, its left should not be smaller. Its left should not be smaller. So this is not a BST tree. Did you guys get it? Why this tree is not BST? Everyone, it's a small thing. Yes. So Parag, the condition was always left side should be smaller than the root. Always left side should be smaller than the root node. So if we talk about this small subtree, so this is our root and this is our left and this is our right. So you can see according to BST, always left side should be smaller. But here we can see it's not. It's not. So that's why. That's why it's not BST. Understood, Parag? Parag? Understood now? You can see 10 is greater. And our condition is left side should be smaller. Yes? Got it? So that's what, guys. I assume wrong. No problem. So that's what actually BST is, guys. Now, because why we have given this why we have given this restriction, it helps us to search our trees efficiently. It helps our searching or traversing efficiently. If we talk about the same tree, and if somebody is saying to find me 11, find me 11, you know, first I will check with my root. Is 11 is greater than 8? Yes, I will not traverse this part of tree. I will only traverse this part of tree now. Right, guys? I will not, because I know my tree is BST. All the smaller will be on the left side. So that's why I will not traverse to the left side of it. I will just traverse half of it. So that's what the benefit gives you, the BST. Whenever we talk about the BST gives you this benefit. You always know that this value could be reside on which side. Earlier in binary tree, you do not know about it. It can be reside in anywhere. It's not sorted, by the way, but yes, if we can say that ascending order or descending order, we can decide it. Yeah, understood, guys? The benefit of BST, that we can reduce our search space, right? In binary tree, our search space was open. We have to search every node, but now in the binary search tree, we do not need to traverse every node. We can compare it with the value, and then based on that value, we can go into the left side or in the right side. If the value is smaller, if the value is smaller than the root, we can go to the left side. We do not need to go for the right side. Similar to binary search. It is binary search only. Ah, okay. This is similar to binary search. Yes, yes, yes. That's right. That's why the name is also similar. Binary search tree. That's right, Hariran. Yes, yes, you are right. Similar to the binary search. In the binary search, we also do the same. We go for the mid element. From the mid, we just go for the left side. Same thing here. Yes, insertion will now make sense here. Insertion will make sense here. Okay. Before moving into the insertion, let's find out the pre-order and post-order also. For the same, like if we want to create any binary search tree, let's create a one binary search tree here. Because now we need to like smartly do the insertion. So we'll take here um, uh, 8. We'll go for 6. You can go for 7, right? We can go for mm, here we can go for 5, correct? Here we can go for 18. Here we can go for 17. Here no. Go for 15. Go for 15. Here we can go for 17. No. 17 can't be here. Here it could be 21. 21 could be here, right? See, guys, how how much we need to think about it now. 13, 14, yeah. Here I think 19 could come. 22 could come. Yeah. Is it a BST or not? You guys tell me, is it a BST or not? I think it is. I have done with thinking, right? It is, right? So Hariran is saying no. Why, Hariran? Where I made the mistake? Oh, yes. I made the mistake here in the 14, right? It should be 17 or 16. Ah, got it, got it. Hariran got it. Yes, yes, yes. Got it, got it. Now it is correct, right? 17 could be there. Yes. Thank you, Hariran. Okay, so now this is the tree. So now, guys, let's calculate the pre-order, in-order, and post-order. I will tell you why I am saying you to do that. There is one thing you will find out in the BST. So first, tell me about the pre-order. The pre-order is, you know that root, left, and right. In order, you know that left, root, right. And post order is left, right, root. Let's do that quickly. So let's start with pre-order. So we start with 11. So 11, then this is the tree, 8. Then we'll go for left side. We'll again got the root, 6. Goes for left side, we again got the root, 5. There is nothing on the right side. There is nothing on the right side. There is 7 on the right side. Okay. Root left already traverse. Go for the right side. 18 is there. Go for left side. 15 is there. Go for left side. 13 is there. Go for right side. 17 is there. Already traverse the left. Already traverse the root. Go for right side. 21 again got the root. Go for left side. Again got the root. 19. Go for right side. Again got the root. 22. Does it look good? Is it correct, guys? 11, 8, 6, 5, 7, 18, 15, 13, 17, 21, 19, 22. Yes. Parag, Arad, you have done wrong. Correct. Node 8. 1 minute. Node 8. Oh, yes, yes, yes. Oh, yes. Sorry, yeah, the Parag is catching is right. It should be 9. Right? Guys, yes. This could not be correct, right? This should be 9. So what was the number here? It was 7, right? Yeah. 7 will be replaced with 9. Correct? Sorry for that. Yes. It looks good right now. Who was saying that? Hariharan. Yeah, Hariharan. It is good, right? Thank you. Thank you again. Okay. Now let's calculate the post order. Let's calculate the post order. So the post order is left, right, root. So first go to the left, 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 left. It will reach to 5. Then right. There is nothing on the right. Go on the back. Go back for this one. So left already traverse, nothing on the right. Root. Root is 6. Right? Let's go above. Left already traverse, go for right, which is 9. Then go for root, 8. So left already traverse, go for right. If I go for right, 18 is coming. We have to go for left. So left, 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 13. Left traverse, go for right, 17. Traverse the root, 15. So left traverse, go for right. Go for left, which is 19. Go for right, 22. Go for root, 21. Left traverse, root traverse, go for root, 18. Left traverse, right traverse, go for root, 11. Is it correct, guys? Post order. Doing it wrong? Oh, you did in order. No problem. No problem. It's a post one. Yes, it's a post one. I want to show you. I want to show you one thing. That's why I did the post first. Okay. It's the post one. Can you guys try for post one? Let's try for post one first. Let's try for post one. Okay. It's correct, right? Yeah. Okay. So now, guys, you guys observe one thing in the in order. So let's do the in order also. So left is 5, 6, 8, 9, 11, 13, 15, 17, 19, 21. No, no, no. 18, 19, 21, 22. See, guys, always in order would be the sorted one. Always. In BST, always in order will give you the sorted binary tree. Somebody was asking from the day one, how can we sort it? How can we sort it? So this is, you can see that you can create the binary search tree and just traverse it in the in order, you will always get the sorted one. Always get the sorted one. That's why I want to show you this thing. That why why the in order is important here. Always in the binary search tree, you will always get it in order in sorted manner. You just try it for anything. Okay, guys. So that's what I want to show you. That's why I went into this part. Okay. Now let's talk about the insertion and deletion in binary search tree. Okay. Now let's talk about those scenarios. Okay. So now let's talk about the insertion and deletion. Okay. So now let's first start with insertion. So now node part you are already aware of. Node part will be still be same. It will contain data. It will contain left. It will contain right. Correct? Node part is same. That is same because it's a binary tree. So binary tree, the same node we will using the same here, but just the condition is different. Okay. So now let's insert 15. Let's insert 15. Correct? So guys, right now we do not have anything in the tree. So like in the tree, we always have root. And root is right now pointing out to null. Correct? When a tree is empty, root is pointing out to null. Correct? So right now, we'll first check that the first scenario, null, simply create a node. Create a node and assign it to root. Now root is equal to new node 15. Correct? This is the first scenario. When tree is empty. Am I right, guys? When tree is empty, this is the first scenario. Correct? So let me show you the code for that quickly. Yeah, you can see this is the code. See, I'm taking current node. My root, I'm taking it as a current node. I'm checking. If we do not have current node, it means my tree is empty. If my tree is empty, create a new node and assign it. Correct? Understood, guys? You can see I'm taking the current node. I'm taking root in the current node because we do not have anything in the tree, so root will be null. So current node is also null. So if not current node, go for the create a new node, new tree node, and add it to the root. Good, right? Now we can go for the next step. Now 15 has been inserted. Now 15 has been inserted, and it root is pointing out to this thing. Correct? Are we good, guys? Now let's look for next element. Now let's look for next element, which is insert 8. Correct? Insert 8. So what I will do, guys, now I will again this condition will fail because now root is not null. This condition will fail. Root is not null. So what I will do here, I will first check with my root value. I will check with my root value. If root value is less than greater. If it is greater, if my root dot value is greater than the new node value, so add it into root dot left. Root dot left. Else add it into the right side. Correct, guys? So after that, if I insert 20, so it will be added at the right side, or 8 will be added at the left side. Correct, guys? this code. Everyone understood? So you can see if root dot value is greater than new node dot value, add the root dot left is equal to new node. Else root dot right is equal to new node. Correct? Yes, I am sending it for the equal condition also. But if you want to consider, there will not be any duplicate element. So then you can apply condition for a greater also. That when element is greater, then only has to go there. But I am right now thinking for duplicate elements also. Okay. So now this is the scenario, guys. Okay. Now let's look for if I want to insert 6 here or 7, whatever, 6 I want to insert. So what will happen here now, guys? Again, it will start from root. Correct? So first again I will check if root dot value is less than 6, less than, yeah, if root dot value is less than, sorry, it's greater than 6. Yes, it is. I need to go to which side? If my root value is greater than the new node value, I have to go which side? If my root value is greater than, I have to go which side? Left side. Yes. So I will go for left side. And I will again check because left side again have one node. So I will check with this node now. I will check with this node. So I will check with 8 now. I will check with 8 now. And I will check that is the 8, the value of root dot left, is it greater than the new node? Is it greater than the new node? If yes, it will go for left side. Otherwise, it will go for right side. So that's what continuously we need to check these things in both sides. So that's what the code is also doing, guys. You can see when root is not null, you can see I've created one function and passing my root there. And in this function, I'm checking if my root or node, like what, because first time root would be my node. So node dot value less than value. Yes. If node does not have any right, like in the first scenario, in the first scenario, root does not have any node. Root does not have any left or right. You can see root does not have any left or right. So simply I'm adding node dot right is equal to new tree node. The logic, this one, this logic, root dot left, this logic, root dot left is equal to new node, root dot right is equal to new node. If my node does not have left, does not have right, simply add it. If my node has left or right, traverse it, and traverse this node till I find a position where I do not have anything, where I got the null. Understood, guys? I will see. I will, if there is 8, there is 20, I will traverse till I reach to this position where I do not have any null here, to the left or to the right. Because every time new element, whatever new element is coming, always be added into the leaf side, added into the leaf node. Correct? Are you guys able to understand? Always a new element which is going to be inserted is going to always be inserted into the leaf node, right? So that's why we will simply traverse it, go for left, go for right, traverse it, and stop only there. Once you do not find left, do not find right, and once you do not find any left or right, you will just add this new node. And how you are going left or right? You are checking the values. You can see every time you are checking the values. If node dot value less than value, you are going for the right side. If node dot else, you are going for the left side. You can see node is every time root is changing. If root की value कम है current node की value से, you just go for right side. If it is greater, go for left side. Understood? Was it difficult, guys? Insertion in BST, was it difficult? Understood, right? Oh, Arad is saying it is. Oh, not actually. Yeah, not actually. Great. So now let's go for deletion. Let's go for deletion now. Okay, guys? Let's go for deletion. Deletion is also, in deletion, there are 3 scenarios. Time complexity for insertion. So time complexity would be, I think, uh, time complexity for insertion. If we talk about, so we are traversing into one side only. So I think it would be log n, log h, because we are traversing into one side only. Let me think 1 minute, 1 minute. So, like if we can count out somehow the number of nodes, and just divide it. So, like if we consider n as a number of node, so log of n would be the time complexity here. Correct? Because we are only traversing half of the nodes in the in the binary search tree. We are just traversing half of the nodes. We are not traversing everything here. If your value is lesser, it will always go into the left side. It will not go for the right side. Okay, so that's what. Okay, now let's quickly talk about, guys. O log n is the worst case time complexities. Yes, but yes, guys, I will just look into this part because in tree, most of the time they talk about the complexity with the reference of height, with the reference of height. So I will look into that part, and I will explain it in the next class with the height. Because people generally ask about in the interviews. I just got it right now when you ask about it in the interviews. When they are talking about the time complexity, they normally ask in the height perspective. So I will look into the height perspective, how much complexity, how they are calculating the complexity for this, and then I will tell you about this. I will talk about. I will look into that one. But yeah, I think there would be something like that, but it has to be reduced, right? Somehow, height or nodes, number of nodes. So I will look into that. So yes, if we talk about the number of nodes, so I think yes, in the worst case, no, actually, this could not be the worst case. In the worst case, it could be n only. If we have a left skewed tree, if we have something like this, Hariharan, one, two, oh sorry, if we had something like this, 10, 9, 8, 7, and 6. Now, if you want to insert 5, you have to traverse whole nodes, right? So O of n would be worst, yes. O of height would be best. Okay. Yeah, it could be as Deepak is saying, could be work that way. But I need to check this one. I will check this thing also. Okay. Best can be one. So one would only be for no root node, right? One could be one could not be there. I think so. One could only be for root node, right? The first element which we have inserted. I believe one could only be that, only be for that. Okay, sure. I will check and discuss it later. Yeah, definitely. Okay, so now let's talk about the deletion scenarios, guys. Okay, those are also a little bit interesting. So I want your attentions there as well. Okay, in the deletion scenarios. So now, do we have previous page? Yes, this is the previous page, right? Yeah. Now because we will discuss in this one only. Okay, let's keep these things here only. This was the pre, this was the in. Okay, guys. So now, in this binary search tree, there are three scenarios for the deletion. Only three scenarios, guys. One, when deleting leaf node. When deleting leaf node. Like this. 5, 13, 17, 19, 20, or 9. These are leaf node, right? This this is the first scenario. If somebody is saying you to delete the leaf node, right? Or if your node which you are deleting is leaf node, then you do not need to do anything. You just need to make that node as a tree, that node as a null. So like if somebody wants to delete 5, you just need to make this node as a null. It will not change your BST structure. It will not change your BST structure. Still you can see this whole tree is BST. If somebody wants to delete 9, just delete this one. Just delete, delete, just put these nodes as a null, 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 null. Simply. Just make those nodes as a null. Understood, guys? Are we good for the first scenario? Everyone understood? See, our purpose is after deleting the node, our binary search tree should not be disturbed. It should still be binary search tree. Okay, so that was the first scenario. Okay, now let's bring this back. Yeah. So now second scenario, if we have single child, if any node has single child, so like this 6, if we want to delete 6, or there is no other scenarios, everywhere double childs are there, or leaf nodes. So yes, in that scenario, when we have single child, left side or right side, just make that node, make that right node to the previous node. Just remove this 6 and make this as a 5. Now you can see still our binary search tree structure has not changed. Still it is BST. Every time. If this, if I just create, if this 22 has a one more like 23, so just delete. And if you want to delete the 22, just make it as a 23. This node as 23 and delete it from here. Delete this one. Understood? The second one also, if we have single child and we want to delete a node, if we want to delete a node which have a single child, so just make that single child as a parent. We are done. Good? Are we good? Yeah. Now the second one, which is little bit complicated, which is if we have both childs. If we have both child, like everywhere in this scenario, everywhere this could come under that, right? This could come under that, this could come under that, this could come under that, and this could come under that. All these nodes can come under that. The third scenario. Am I right, guys? All those nodes can come into the third scenarios, right? So now in this scenario, they are telling two ways. They are telling two ways. Whatever node you are trying to delete, whatever node you are trying to delete, take the in order successor of it. In order successor of it. So like for 11, if we want to delete 11, if we, let me first remove these things. Yeah. So if we want to delete this 11, so in order successor of it, successor means after that, whatever the in order successor is. So like see, in the in order successor, after 11, 11th in order successor is 13. So just replace it with 13 and it will not change your binary tree structure. So just replace this one with 13 and yeah, you can see still your BST is maintained. Still your BST is maintained. Anywhere, not here only. You just check for 18 also. 18 in successor is 19. So if we want to delete 18, just replace it with 19. It will not change. Same for 8. For 8, it's 9. So just replace with 9. It will not change. Just check it anywhere. You guys check it. Just you have to replace it with in order successor. Correct? And you know that in order successor is, okay, once again. So guys, for deleting Hariharan, it was Hariharan, right? Yeah. So Hariharan, for when we have a node which you want to delete has two childs or both childs, left and right. So in that case, check for in order successor of that node. In order successor of that node. And you because see why we are looking for in order successor. Why we are looking for in order successor? The reason for that is I already told you in order traversal always gives you nodes in a always gives you a node in a sorted manner. In a sorted manner. So always whatever node you are looking for, the next element of it would always be greater. It would always be greater. Like if we simply 4, 5, 6, 7, 8, 9, 10. If this is the example, I want to delete 7. If I want to delete 7, so so the next element to 8 will always be greater than the left element, or will always be lesser than the right element of it. Correct? 8 will always maintain the same situations. 8 will always maintain the same situation. Am I right or not? Next highest element, yes. Or successor, because the in order will always give you the next highest element. Yes, next highest element. Yeah, for 18 it is 19. Yeah, for 18 it is 19. So just replace it. 19 will come here and 18 will be replaced. See, still it is maintaining the BST. You see, is it not BST now? Yes, it is, right? Yes. Clear now? So see guys, you guys tell me, for finding out the, if we do not have in order traversal, for finding out the minimum, finding out the in order successor, I think you just need to find it out minimum element in the right side of subtree. Minimum element in right side of subtree, and it will always be in order successor. It will always be in order of successor. The minimum element in your right subtree, the minimum element in your right subtree will always be in order successor, because it will always be in the left side. You can see that, right? With this example, if this is the 7, if the right tree is this, so minimum element will always be here, right? See, with this data only you are just with this data only you are just making these assumptions, making these facts, not assumptions, these are facts, right? These are facts. So now are we good, guys, for all those scenarios, all three scenarios? The first scenario is very simple. If we have any leaf node, if we find out anywhere leaf node, make that node as a null. Make that node as null. Second scenario, if we have single child, so make that root, make that root as a left or right. Make that root as a left or right. And for the third scenario, when we have two childs, so we need to find the in order successor. In order successor, you need to find or the minimum in right side of subtree. Minimum in right side of subtree. In order successor or minimum in right side of subtree. For that node, there is right subtree. So in that right subtree, just find out the minimum and then replace. Then replace that node with the right side. Okay, are we good, guys? One child. So for one child, where was the one child? Yeah, 17 is one child, right? For 17, for if you want to delete 15, if you want to delete 15, it has one child. So just replace this 17 with this 15. That's all. Replace that root node with childs. If it is left side, then we need to find in order successor in left, right. Left. If it is left side, then we need to find in order successor in left. No, no, no. In order successor, you will always find on the right side. If it is left side, I didn't understand. If it is left side, then we need to find in order successor in. In order successor will always be on the right. Successor means next element. If we need to delete element in left. I didn't understand your meaning of left. What is left here? We have only three scenarios. Leaf node, one child, two child. What is left here? If we have two childs, we need to look for the in order successor for that element. And in order successor will always be on the right side, on the right subtree, minimum element in the right subtree. In some scenarios, pre and post, yes, pre and post will change. Definitely, Parag. Pre and post will definitely change. Yeah. Okay, so now let me show you quickly the code also, which is written in recursion for that. Okay, so this is the remove function which we are calling because they have written in the recursion. That's why things are happening again and again. Okay, so now you can see if node, so I'm checking, like I'm passing my root node, right? So now root node is coming here. So now I'm checking the value which we want to delete, the value which we want to delete, like 11 or 15, whatever you want to delete. We are checking if value is less than the node value. Right now we are in the root. If it's if it's a less than, we have to go to the right. We have to go to the left side. You can see we are traversing on the left side. Correct. And if it is greater than, then we are traversing on the right side. Correct. These two things are happening, and you can see that the when we are traversing on the left side, and if we got anywhere single child, if we got anywhere a single child, you can see I am just making that that child as a null. I'm just making that child as a null. Node dot left is, see, because at the end you can see this is returning us what this function is returning. You can see this function is ending at this place, right? So this function is returning a node to us. So node dot left is equal to node dot right is equal to node. This will be returning that node to us, correct? And you can see at the end, node dot left or node dot right, any one of them could be returned to us. And this will happen for both scenarios, for single child also or for the leaf node as well. Because see, for the leaf node, the node dot left and node dot right will be null. For the leaf node, node dot left will be null, node dot right will be null. So we will be returning null at that place. So we will be putting null, or might be the, or in the single child scenario, we will be returning the node dot left or node dot right. And this is the second part of code where we are going for, if we have child, like both childs, node dot left, node dot right. So first we are finding on the minimum value, and just you can see I'm just passing the node dot right, not node dot, because you know that in order successor will always be find, you can always be find on the right side of that. And you can see in the find min value, we are what we are doing, we are taking that value root dot key, first making it as a minimum value, then we are checking, because root dot left, only left will have that successor, you know that, right? In the in order successor, in order, how the in order work, left, root and right. So on the right subtree, you just need to look for left. You know that, right? 13 was on the left side. This 13 was on the left side. Always be, in order successor will be on the left side. Always be on left side. That's the in order means left, right, root. So that's why you can see I'm just simply making I'm just traversing root dot left every time, and then making my minimum value as a root dot left dot key. Wherever at the last I will stop, I will take that as a value. And then at the end, I am passing my node dot value, which is this one, which which we want to replace, and then the node dot write. Correct? Node dot value and node dot write. So this code is little bit actually complicated to understand also. For the second, yes, for the second scenario, actually they have made it in both scenario. In this one, they have made it in this one only, both scenarios. So this is actually, this code is little bit complicated. Actually, I will write my code also, my code again, this one. See, this code is also working in a similar way, guys. This code is also working in similar way, but they have made little bit complicated to understand. See, the second scenario and the first scenario, all are happening here. Once the node dot left is null or node dot right is equal to null. So at that time, node will be null. This is the first scenario. And in the second scenario, when we have only one child, so at that time, we might be returning in this node dot left, we might be getting left value because we can have left single child or we might have right single child. So in that node, we will be having that. And above, we are simply traversing it. And after traversing it, we are setting left or right for that node. Correct? And in the last one, we are just first finding out the value on from the right side. And then once we find it out, we are setting our node dot right. So this code is little bit complicated. This code is little complicated. I have not created the new code, but I will create it, and I will suggest you guys also to create your code with all those three scenarios. Okay, and then we will in our next class we can just go through with my code as well. But yes, I will first suggest you, because see, in the logic part, do you guys have any confusion? In the logic part, do you guys have any confusion there? No, right? Yeah, so please try to generate this code from there, from your side. Yes, and once you generate it, please post it in the LinkedIn. I will see that. Okay, yeah, great. Now let's go for next question. Now I think, now actually this is all about the BST. Now problems will start. We have to solve the problems now. Okay, so now I think the first problem is print the, you will explain your code in next class, but I'm assuming, Joseph, I will be explaining your code, not my code. I want you to generate a code for this and then post it into the LinkedIn. I will explain your code. Okay, in next class. So just please try to generate your code and then we will talk about your code. Yeah. Okay, so now let's look for the next problem, guys. So we are given a binary tree or binary search tree. We have to print the right view of it. Okay, so now this question is saying we have a tree like this: 1, 3, 5, 4, 2, 6, and 7. Okay, guys, they are saying print the right view of it. Print the right view of it. So just consider one man is standing here onto the right side. This is the right side. and this is the left side, right? So from the right side, how many elements he can directly see? How many elements he can directly see? If this is standing it here, how many elements he can directly see? I think he can see this one from the right side. He can see this thing. He can see this one, and he can see the this one. Correct? From the right side, he can see this. Just imagine it. From the right side, you do not, because five will become a window. You cannot see these two, these three. Three will become a window for this. Five will block this one. So in one way, if we say, so the right view is in each label, just print the last element. In each label, just print the last element. Is it right observation or not? Yes, engineering graphics, engineering design, or there was one class in engineering classes, ED. Yeah. Okay, so by the way, so yeah, so it is asking us in each label, just print the last node. Can you guys do it or not? Because you know that how to go into each label. You know that how to go into each label, and you also know that when would be the last element will be there. When would be the last element would be there. No, this is easy, right? Take a q, take a size variable, and this size will put the while loop here. Correct? So now first we will put this first element 1. Now size would be 1. Correct? And now we will do size minus, see, we will do size minus 1 as the first. Size minus 1. And then we will check if size is equal to 0. It means we are traversing the last element. We are traversing the last element. We are traversing the last element. And this time we will simply console it. Console.log node.value. Correct? So now second time when we will be having 2 comma 3 here, I just given you answer now 2 comma 3 here. So now size will be 2. So now first size minus 1 will become 1. 2 will be removed. Right? Now size will become 0. At that time 3 will be removed and you will print the 3 here. So now first printed 1, then 3, then 6, 4, 5 will go. 6, 4, 5, size will become 3. Correct? So once size will become 0, you will be reaching at 5 only. Correct? Yes, at each level we need to get the last element. I have showed you the code only. I have showed you the code. Yes, size and that wing. It was easy, very easy actually. And in similar way, there is also very easy questions, which is in order only, but in different way. Yes, same approach. There is one more easy question actually, which is the last question. What are other questions? Check if it is a BST. Guys, can you check this thing? How to check a binary tree is BST or not? How to check if binary tree is a BST or not? In each node, you need to check two things. Okay, I will give you an approach for this also. Yes, that's what. Okay, let's talk about it. Correct? Okay, so now if I'm at this node, guys, and if I want to check this node, so okay, when I'm going to the left side, always there would be one condition left should be smaller than the node, right? And right, and if we talk about this element, right should be greater than the node, correct? If I'm talking about, yeah, that's also one way. But if in one traversal only you want to know, because first you will make in order, that will be one traversal. Then you need to check if it is sorted or not. Then again traversal. That's not good way. Correct? So see, in this way only, what you need to do, you have, because you know these conditions. So what you need to do, you have, while you are traversing, while you are traversing, just give them minimum or max. Just give them range. Just give each node a range. So like if I'm saying for the root node, I'm giving it as a minus infinity, and plus infinity. This is the range. So 10 should be between these two. What about 9? What would be the range for 9, guys? You guys tell me what would be the range for 9? What would be the range for 9? 9 could be between what? Nobody is responding. Between 8 and 10. No, no, no. So 9 could be between minus infinity, comma 10. Because 10 is starting from minus infinity. See, I'm taking minus infinity, comma capital infinity. So it could only be between these two. Minus infinity, comma 10. 8 could be between minus infinity, comma 8. Or comma 9, sorry, comma 9. It should be always be lesser than 9, right? Or I think, see, it should be less than root 9, because it could not be 10, and it could not be 9, it could 9 minus 1, correct? And same here, it could be 11 comma infinity, and it could be 12 comma infinity, greater than that, because we want to look for greater than. So right now what I'm saying here, whenever we are traversing, just look for these ranges. Just look for these ranges. Understood, guys? Just look for these ranges. And I have the code for as this as well. Is valid BST. Yes. You can see if node dot value less than min or node dot value greater than max, return false. And you can see in the form method, I'm passing number dot min value, which is minus infinity for the root, and number dot max value. And then every time I'm updating, you can see each BST for the node, for the left side node, passing minus infinity, minimum, same minimum. But for the max, I'm passing node dot val minus 1. You can see node dot val for 9, I am passing node dot val minus 1, because I am checking for this node, I am checking the left side. You can see for the root node, I am checking the left side. So for the left side, I am passing this value minus infinity, comma 9. For the right side, you can see for the same node, I am passing for the right side node dot value plus 1, comma max. And wherever any value, if I find it out any value which is not between these ranges, I will say that if somehow if I'm putting 10 here, I will say that this is not a BST. That's why you can see if node dot value less than minimum or node dot value greater than max, anywhere I got, I'm just returning as a false. And this is the if node is equal to null, like the if I reach to this place, leaf node, so I do not need to go any other further. So for this scenario, I'm passing true, because node dot left will be null. So for that node, return true directly. If node dot right also null, for this node dot right also. So if I'm talking about this node only, so node dot null will node dot left be right, node dot left will be null, node dot right will be null. So for that scenario, I'm returning both places true. Understood, guys? Code is easy. Code is easy for that. Node dot val minus 1 and plus 1. See, Hariharan, node dot val minus 1, because we are saying it should always be lesser than this. Left should be lesser than this. and right should be greater than this. So how we will make it? So lesser than means 10 minus 1 and greater means 10 plus 1. So at whatever node we are, yeah, it's clear. Yeah, we will always take root as a base. Yeah. Okay, we have 3 more minutes. So guys, I'm not sure Anshul has told you or not, but I think he has already told you. I'm not taking tomorrow's class. I will be now meeting you guys on Monday directly. He has told? Okay. He has told. Great. So now there is fourth question also. See, similar question, guys. If you guys want to try, similar question is 3 as well. We have given a pre-order traversal, find the leaf node of BST. Same code will work there as well. But yeah, we'll talk about this one. This one is little bit medium complex. So I'm not going to talk about it. But yes, last one is easy. Last one is easy. So actually in the last problem, okay, I think question is little bit like last one is easy actually. You guys can try it. In the last one, in order is only in order has to do, but in order in different way. Okay, let me explain you the question, so then you guys can do it in your home. So what they are saying, they have given in one BST. We need to convert this BST in a greater tree, and we need to convert this BST in a greater tree where any of the key if we talk about, we need to replace it with some of all the keys greater than that. See, if we have a 4, 6, 5, 7, guys, because BST is easy. So BST provides you a lot of things. 1, 0, 2, and 3. And this was at the right side. Okay, so guys, what they're saying, you need to replace all these nodes value with the greater value. And how will you find out that greater value? Go to any of node and find out all the greater node of it, and add all those greater nodes and then replace the value for it. So like for 7, greater node is 8. So add these together. So 15. So 15 will be here. For 8, there is no greater node. So for this 8 will be there. For 6, how many greater nodes are there? 7 and 8 only. And include this one also. So it will be 21. For 5, how many greater nodes are there? 6, 7, 8. So 6, 7, 8 is 21 and 5, 26. So it will be replaced with 26. Same goes for 2. How many greater nodes are there? All these are 1, 4, 6, 5, 7, 8. All these are greater nodes than them. So for 2, 3 is also greater than that. So for 2, so for 2, add all these nodes. 3, 4, 7, 5, 12, 6, 18, 25, 33, and 35. 2, 35. So this will be 35. Understood, guys? For each node, add all the greater nodes and replace it with there. That was the question only. Understood the question, guys? Everyone understood? You just need to look for all the greater nodes of them, add them, and put it here. So guys, because it's a BST, where will be all the greater nodes? Where will be all the greater nodes? Yes, on the right side. On the right side. So yes, so start traversing from the right side. Start traversing from the right side. Yeah. So start traversing from the right side. So for 8, all the greater node will be on the right side only. Correct? For 8, all the greater node would be on the right side, but there is no greater node. So 8 would be 8 only. It would be 8. For 7, traverse all the right side, which is 8 only. So add it with the current node. Add it with the current node, which is 15. right? Which is 15. Now go for 6, all the right side. Again, all the right side. So 15, we already traversed the 15, so it will be 21. For 5, because it is on the left side, it is on the left side. So before that, whatever is here, it's all greater, right? Before that, all of, see, you know that, right? In the BST, left side is smaller and all of them, including root, it's also greater. So we just need to add the 21 plus 5, 26. So guys, it is nothing, it's just the in order only. It's only in order traversal. But in order traversal, you traverse like this: left, root, and right. But here you are traversing in right, root, and left. In similar code, you are just traversing right, root, and left. So first you will do like this. I'm just writing the recursion code. So if node dot right, traverse it. If node dot right, in order, node dot right. And once you reach, just take one variable as a current sum. So once you reach to the last node, which would be 8, then then add current sum is equal to current sum plus node dot value, and then traverse the left side. This is the code actually. Same in order code, but just in opposite way, right, root, left. And this current sum, you can update it in the same node. You can update in the same node. Node dot value is equal to current sum. You can update it. That's what you need to do, guys. Understood? Was it difficult? Was it difficult, guys? You just need to traverse from the right side. Take one variable and update your current sum. It's like simply like if you have an array, you have to go from the back side and update each index. Okay, so that's all from today, guys. I've just given you some of the hints. Some of the code is already available uh, in the branch. So I will push it in front of you. It's in the master branch, BST. Now you have 3 days, guys. So please practice it. And please share your code and doubts and queries in LinkedIn group. Okay, guys. So now we'll meet on Monday. Have a good weekend, guys. Good night. Bye bye.